Okay, so welcome back. Today we are talking about classical linear models. We already pitted some linear models yesterday. Yeah, so let's start. First, we are kind of defining what is a linear model. Then we are talking about continuous predictors, which we usually associate with the name linear regression. Then we move on to categorical predictors, which sometimes goes under the name ANOVA. And then the mix of continuous and categorical predictors is sometimes called ANCOVA. And I want to take the opportunity in between to touch two kind of important topics which fit nicely here and which I can illustrate quite nicely here with the linear modeling framework. And this is first of all model selection, and the second one post hoc analysis. This basically means making or averaging predictions after fitting the model to answer some specific questions. So what is a linear model? So we have already seen the linear regression, or this kind of linear function, a plus b times x, where x is the variable and a and b are constants here in this case. So this is a linear function. There are many other functions which are not linear. For instance, 1 over x, this is not linear. X squared is also a nonlinear function. And other classical functions like the exponential or the log. However, this is just the definition of a linear function. Linear models are a bit different, surprisingly. But first, I want to say linear functions, you can easily extend them to multiple predictor variables. You can just add a second constant times another predictor. And here, since we only have two predictors, I can try to display this in a fancy 3D figure. But if you add more predictors, you can't kind of display this anymore in any meaningful way. However, you can always display the function against one of the predictors for different levels here of the second predictor, or the other way around. So these lines are just cross sections, either here sliced along this x1 direction, or sliced along this x2 direction here. Okay, that's the linear function. However, linear models are related, but they're not exactly the same. Here, the linear functions, we care about if it is linear in the predictor. So it's a linear function of x. But the linear model actually means that the model or the function is linear in the parameters, which is the case for just a simple regression line. It is both linear in the parameters, and it is also linear in the predictor. But for linear model, it is linear statistical model is defined to be linear in the predictors. Linear in the parameters. Right, so here's just one parameter, and the second parameter is just added and multiplied with the predictor. And additionally, a linear model also has an error term, which is the residual. And in the linear model, usually we assume that this is a normally distributed. Also, if you extend this to more predictors, this still is a linear model, because here we just have 3 parameters and the model is linear in all of these 3 parameters. So in frequentist statistics, this is kind of very convenient because there is analytical solutions for estimating the parameters. So yeah, you can do maximum likelihood, but you don't have to, because there is kind of like a closed form formula for directly calculating the maximum likelihood estimate, which is automatically done with LM. There are other examples of a statistical model that can be nonlinear. For instance, if the model is some intercept plus some predictor to the power of something. So we want to estimating this power function here. And this is nonlinear in the parameters, right? So it's not, I mean, it's also nonlinear in the predictor, but the important thing here that it's nonlinear in the parameter. So this is a nonlinear model which you cannot fit just with Ln. Or if you have some exponential function, e to the power of b times x, again, this is nonlinear in the parameter. And here, maximum likelihood has to be used to estimate these parameters. Sometimes a nonlinear function can be a linear model. Most famously, polynomial relationships, so quadratic regression, or interaction effects. So these are still linear models. So let's look at the first example here. This is clearly a nonlinear function for the predictor x. If you look at the first equation here, it is b0 times b1 times x plus b2 times x squared. So this is clearly a nonlinear in the predictor. However, it is still linear in the parameters, right? There's just one parameter added plus the second parameter added with x plus the second or the third parameter multiplied with x squared. So it's linear in the parameters, and we can just define x squared as a new predictor, which is x2, and then this looks like a completely classical linear model. The same holds for an interaction effect. Here, this is nonlinear in the predictor values. Right, so we multiply both of the predictors, so this is a nonlinear function. Also, you can look at the 3D plot. This is not a kind of plane anymore because it's kind of warped. However, it is a linear statistical model because it's linear in the parameters. We can just define a third predictor, which is the product of the first and the second. And then this looks like a classical linear model. Yeah, sometimes with the transformation of the response, you can turn something into a linear model. For instance, if you look at this is just a linear model, right? For if I predict log of y. So classic linear regression here, nothing fancy. But if you transform this back to the original scale of the data, this means putting the exponential function around this. So then you have just y here because exponential is the inverse of log. But this part here turns into some exponential function, or you can write it down with a new parameter. So this is some scaling parameter times e to the power of bx times, now the error becomes multiplicative here. So this looks like a highly nonlinear function, both in x and both in b. But you know, if you transform this back to the log, right? So if this is your model, you know, by log transforming it, I can turn it into a linear model. So sometimes statistical models can be linearized by transformation. And even here in this case, look, the error here is multiplicative. This means that at low y values, you have kind of small variation, and at high y values, you have large variation. So this looks like a kind of horrible model to fit because all the assumptions are not met. However, if you transform this to the linear scale, here the residuals are constant, and it's a classical linear model. Why are we using linear models, or especially in frequentist statistics? Well, all kinds of common tests are basically just linear models. For instance, I didn't come up with this with myself. This is the reference where you can find this nice overview. So here are simple linear regression models with just one predictor. Here are models with several predictors. And all these things that have like a fancy name, like, okay, I'm doing an ANOVA, I'm doing a Kruskal-Wallis, I'm doing ANCOVA, two-way ANCOVA, and so on and so on and so on. They are basically just, I'm fitting a linear model with, I don't know, a couple of predictors, maybe continuous or categorical predictors, and I'm performing statistical tests of the model versus a reduced model. And all of these kind of fancy names are all contained in this very general framework of linear modeling. But in Bayesian statistics, linearity is actually not that important, because we are sampling the parameter by MCMC anyway. So the MCMC does not care about linearity of the model, right? It can just sample from, in each iteration of the MCMC, you compute the model predictions, and then you calculate your likelihood, you multiply likelihood by prior, and so it just has to do the model prediction here. It just has to calculate the model prediction, and it doesn't, MCMC doesn't care if the model prediction comes from a linear model, so linear in the parameters, or from a nonlinear model. So there's no actual benefits in Bayesian statistics for having a nonlinear model versus for having a linear model versus something else. However, in the sense of good scientific practice, you only should kind of move away from linear models if you have a good reason. There's the classical principle of parsimony, or also called Occam's razor, very old scientific concept from 14th century, and the literal quote goes, "Entities must not be multiplied beyond necessity." And this also means that here you shouldn't go fancy with your models or with your kind of deterministic part of the model if you don't have a reason. If you just want to estimate a relationship, your first go-to should always be a linear model, and then you can after fitting the model still think about if this is a good model or not. But this should be kind of the first choice in the sense of good scientific practice. So let's talk first about continuous predictors only. This is what we had so far. Yeah, we already talked about the response can be continuous or discrete. We talked about parameters being continuous. Here we only deal with continuous parameters, no discrete parameters involved here so far. But also the continuous can be continuous or categorical, but both of them can be treated in the framework of linear regression. So what I'm showing here in the most part of this lecture is not necessarily connected to Bayesian statistics, but yeah, you can see it as a summary of linear modeling in general, and you can either use Bayesian statistics or frequentist statistics to estimate parameters there. So let's start with a single predictor. That's the classical linear regression, and we've talked about it a lot already. Yeah, we yesterday actually fitted the data set. We have we assume a latitudinal gradient in plant size and the global database, where the log of plant height is the response and the latitude is the predictor. Later, we will also include a second predictor as well. So the statistical modeling, again, always think of deterministic and stochastic part. Here, the deterministic part is my linear regression line. B0 and B1 are the parameters. These are intercept and slope. And the stochastic part is that my predictor log height, my response log height is normally distributed around the mean prediction. Okay, yeah, well, we can easily fit this with LM, or we can use brms. And then we get some output. with some parameters here. And here, these parameters, they have a very specific meaning, right? So the intercept, this is the value where the predictor is 0, right? So if the predictor here is 0, this cancels out, and the prediction is just be 0, so the intercept. So in this case, this intercept is actually meaningful because latitude goes from 0 to larger values. And here, the intercept is the predictions at the equator. So here, the intercept actually is meaningful. Often, if you have data which are far away from 0, then the intercept is not meaningful because it's just a prediction outside of the range of your data because 0 is far away. But here, this actually, the intercept is a meaningful value. It's the predicted plant height at the equator. The second one, latitude, that's how much plant height decreases when I increase 1 degree in latitude. What you can do what often makes sense is to scale the predictor. This involves 2 transformations. First, I mean center the predictor. So I subtract the mean of the predictor. This means that the new mean of the predictor is 0, and I divide by its standard deviation. This means that the standard deviation of this new predictor is 1. So your data will usually be centered around, it will definitely be centered around 0, and often the data is around the intervals -2 and +2. Internally, BRMS always kind of mean centers it anyway, just to be computationally more efficient to estimate the intercept. And afterwards, it scales the predictor back to the original scale. But we can also just have some reason for doing this, because for us, all the parameters become more meaningful. So if I kind of standardize my predictor, so I shifted it and I also scaled it down or scaled it up, depending on the original scale. These parameters have a new meaning. So the intercept will then be the mean prediction when the data is at its mean, or the mean prediction for the mean of the data. And that, for instance, makes it easy for us to assign meaningful prior if we want to. BRMS does this automatically, but if we have some other reason to change this, this is a way of kind of having a different parameterization, which is more meaningful. And also the slope now has a different meaning. It means how much does the response change if I change the predictor by 1 standard deviation. And this also makes it easier for me to assign priors, right? So if from some other analysis I have standardized effect sizes, then they can be used to inform the slope here. And if you have like a standardized predictor and also kind of have a standardized response, then you expect your slope to be not too far away from, let's say, 0, or it's very improbable that you have like a slope of 5. So this kind of narrows down the meaningful values, or the values that make sense for the slope. And it becomes especially more convenient if you have more than one predictor. So you can imagine that just latitude as a single predictor for plant height, that's a very bad model because there's, I mean, it's not bad, but you know that there's much more other information going into plant height, for instance, rainfall. And we can add this to the model to get better model predictions and better estimates for the parameters. Here I already scaled down both of the predictors here. And then if I look at the conditional effects plot here against latitude, I can make prediction lines for different values of my second predictor. Here by convenience, BRMS uses 3 levels of the second predictor, which is the mean, and it's +1 standard deviation, it is -1 standard deviation. You can also choose different ones, but this is the default here. And in this case, we see what the parameters mean in this case. So again, the intercept, this will be the value when both of the predictors are equal to 0. So it's when latitude is equal to 0, or the scaled latitude is equal to 0, and also the rainfall is at 0, or at the scaled rainfall is at 0. So that's the intercept. And here in this case, rain. So if I just look at latitude, or the plot of response versus latitude, then the second predictor, rain, tells me how much the prediction changes the intercept for these 3 regression lines here. So you can write out the equation by just rearranging the terms. And then the new intercept for this plot here is B0 plus B2 times rain. So for each value of rain, this regression line in latitude will have a different intercept, and a positive effect of rain here just means that the intercept increases with rainfall. You can also plot it the other way around. Here we have regression lines against rainfall for different levels of latitude, and you can rearrange the terms again such that here only rain is the variable, and for different values of latitude you get different intercepts here. Okay, one thing which is, I think, at least for me, I would say quite important, and it's easy to forget about it. And this is what do these effects actually mean? So the slopes, because often our predictors are not completely independent. But this is not an issue if you remind yourself what the fitted model actually says. Okay, we have the situation here, x1 is latitude, x2 is rainfall, and both of them have an effect of plant height. But then, okay, latitude and rainfall are not independent. I mean, there's some correlation. In this case, there's also very clearly a causation because latitude influences rainfall. Rainfall does not affect latitude. So there's a clear flow of information here, and x1 and x2 are correlated. So usually a bit of correlation is okay. You can just fit the model of log height versus latitude and rainfall, but be aware of the interpretation of the effects. So each effect, for instance, the effect of x1 on y is B only when I keep the second predictor fixed, right? So in your data set, usually if you increase x1, then on average you will also increase or decrease decrease rainfall. So in your model, you must be aware of what kind of predictions you are doing. And that these effects are only valid or only tell you the effects, what happens if I change one predictor while keeping the other one constant. If you want to make meaningful predictions, for instance, some prediction at, I don't know, at the equator versus, I don't know, at some latitude, which is Central Europe, in your model, you should also make predictions where kind of the rainfall is chosen at levels which make sense for these locations. Okay, yeah, and there's a link. I mean, this is a bit connected to structural equation models, where you can separate out these different paths, but you do not always have to go full structural equation model. If you know what your predictors or what the effects actually mean, you can often just fit a linear model and be good with it. One last way of analyzing this data here with these predictors would be to include an interaction. And interaction now means that these different regression line, so this regression line versus latitude for different levels of rainfall, they will not be parallel anymore. Or rather say, I allow some more freedom in the model for them to be not parallel and yeah, to actually increase or decrease in slope. And this is what this third variable here says. So this is how much the slope in latitude changes while changing rainfall, or the other way around. You can again rearrange this this model equation of the deterministic part of the model, and then have some term for the intercept, which again changes with rainfall, just as in the model before. But now also the slope depends on rainfall, and this is expressed by this third or by this variable B3. And I want to note that another advantage of at least centering your predictors. This is really convenient if you're dealing with interactions. Centering your predictors makes your all your variables be more meaningful, because there's these two variables, these two parameters still, the slope of latitude or the slope of rainfall. They are called main effects. However, it's important to know what they mean. Here, the main effect means what is the slope in latitude when the other predictor is equal to 0. And this is meaningful if you have mean-centered your variables, because here then you see, okay, it's at latitude, this is the slope when the other predictor is at 0, and if you centered them, it's when the other predictor is at its mean. If you do not mean center your predictors, this main effect sometimes is completely meaningless, because it just means, okay, what is the slope in variable 1 when the second variable is at 0? And the 0 can be very far away from the data, so this main effect can be very meaningless. So using at least mean-centered predictors can make your models easier to interpret. Okay, so this all holds for frequentist models as the same for Bayesian statistics. So what is Bayesian about it, or what can we do with Bayesian statistics here? there's often solutions for violations of model assumptions. And the cool thing is here you can do all of this in the same package. You can do all of this in BRMS. For instance, if you have outliers, this means that sometimes your residuals are a bit larger than expected for single data points, and a normal distribution doesn't describe this residual distribution well. You can use a student t-distribution, which looks like a normal distribution, but assigns a bit more probability mass to the tails, so to the values which are a bit farther away. And this can help you to get unbiased estimates for intercept and slope, even in the presence of outliers. Another classical model assumption is constant residual standard deviation, also sometimes called homoscedasticity. And if this is not the case, it is called heteroscedasticity. And this also can bias your the estimates for intercept and slope or other effect sizes. So you should account for this. And this can be done by, for instance, a distributional model. I think in the GLM lecture next week, I have an example where you can make the standard deviation itself be a function of some predictors. So you allow that the standard deviation itself can change in your data set. Yeah, then classically, often you have spatially or temporally autocorrelated residuals. And here you can all accommodate this in just one package. You can also do this in classical frequency statistics, but it works quite well in Bayesian statistics. Yeah, this so-called post-hoc analysis in Bayesian stats, you get exact estimates also for your uncertainties. So comparison of differences in intercepts and slopes. Or if you have several groups, averaging across groups. You can always kind of calculate this from predictions and get an exact quantification of your uncertainty. You can either do this manually by calculating predictions, or as we will learn today with the EM means package, which automatizes things and makes your life much more easier. Yeah, including prior information. Okay, this is very general in Bayesian statistics. It's nothing specific to linear regression. But one thing I want to emphasize is if you have small data sets, so if you just have 10 data points, I would always prefer a Bayesian analysis over a frequentist analysis, because you are sure that the uncertainties and the probabilities and so on, that they are correct with Bayesian statistics, whereas in frequentist statistics, just with 10 data points, you can never be sure if your kind of confidence intervals or the p-values are estimated correctly. Another extension, this also works in the BRMS package, is if you have more than one response variable and you want to fit them all in one data set. This is also pretty neat and works well in BRMS. Okay, yeah, just some specifications where I think Bayesian stats can be of advantage. However, I must admit, if you have like a very classical linear modeling framework and sufficient data set and data fits the model fits the data well, then frequentist statistics is just as fine. So I don't want to kind of force you to switch to Bayesian statistics. Just be aware of some pitfalls there. Okay, one last topic I want to address before the quick break, and this is model selection. So first, let's try to remember what is done in frequentist statistics. Often we are performing F-tests to compare different models and to decide which one fits the data better. Frequentist F-tests, they compare basically R-squared values. I mean, it doesn't say explicitly, but basically they're just comparing something with the sum of squares of the residuals and so on, and they're basically a measure of comparing R-squared values. These R-squared values, so the amount of explained variation, will always increase if you add predictors. So the R-squared value can't get worse if you add predictors in a linear model. However, you want to be sure if this increase in model fit, in model fit, if this is kind of statistically significant or just due to some random noise, and then you make a classical F-test of the one model versus the other. We are not performing these kind of classical tests in Bayesian statistics, but we have an alternative. There's actually several, but I will only use one of them here in the course. But first, let's have a quick look again at the F-tests in frequentist statistics. Here, if you look at the classical summary output of such a linear model, you see some p-values. What does it mean? Okay, a p-value means I test the model against the null hypothesis that this parameter is actually 0. And then I get a p-value for it, and if the p-value is small, I can reject the null hypothesis that this value is 0. However, here in this interaction model, you have these so-called main effects, and you're just testing if this main effect is 0. However, this is not very meaningful if you have this involved in a higher order interaction, for instance, in this classical interaction. So you wouldn't use the p-values of a main effect to test if you should keep this predictor in the model. This is just not a meaningful comparison. Therefore, in this interaction model, I would look at the ANOVA table, which is a display or performs tests a bit in a different way. And here the ANOVA table is just 3 different tests. And it starts with a kind of very basic model where you just fit the intercept, and you test if the first variable should be included, here latitude. So the first F-test is the latitude model against just the intercept model. Then the second line tests if you should include rainfall. So it tests the latitude plus rainfall model versus the only latitude model, and so on. And you get your F-tests, your p-values there. And here the last line, this is the only line which is identical in both of these summary tables. Here tests if you should additionally include the interaction over this additive model. And here the answer is no, this model does not improve the data much. Sorry, this parameter or this interaction does not improve the model fit much, so we should not include it. Okay, yeah, F-tests, they have some limitations. They are useful in linear models, but not so much in GLMs. And also you can only use them for nested models. So in frequentist statistics, there's a workaround, or there's another method. It's called AIC, Archaic Information Criterion, which is much more flexible, and we have a version of this in Bayesian statistics as well. It is likelihood based, so it can also be used for generalized linear models. And it has two terms. One term comes from the likelihood. And the larger or the higher your likelihood, the better your model. Here, this is multiplied by a negative number, by -2, and this means lower ARC values are a better model fit. However, this is kind of penalized with model complexity. So K is the number of parameters, so model complexity is included here. Because we know whenever we include predictors, the likelihood will kind of increase. However, it also comes with more parameters. So we have to find this kind of sweet spot between good model fit and model complexity. Here on the right-hand side, you can see that the AIC, or sorry, that the R squared increases for the model complexity. So you would, you could, if you just look at the R2 value, the last model is the best one. However, if you look at the AIC, you see that the last model has a higher AIC. So it means the model in the middle has the best AIC value. So this is the preferred model. And this again is connected to the principle of parsimony. You should only include parameters or include predictors if it doesn't, so if it increases the quality of the fit but does not add much to the complexity anymore. And this is reflected in the AIC value. And we have a similar measure in Bayesian statistics. It's called the leave one out cross validation. And I would, for practical reasons, you can just think of it as AIC, I would say, very, very roughly. It computes the expected log predictive density. This means the expected improvement of model fit when including another data point can be computed from the likelihood and posterior. And it also includes parameter uncertainty and penalizes the model complexity. And here, models that have a higher ELPD are better, but to ease the transition for people familiar with AIC, this information criterion is -2 times ELPD, and this is this can be used just as AIC. So here you see the model. Also, the values are for the most part very similar. And again, here you see that the model in the middle has the lowest LUIC value, so the lowest information criterion, and this should be the preferred model. And it's very easy to use this with brms. There's just a function that calculates this for you. For instance, if you want to test two models against each other, one is the additive model, and the other one is where you have an interaction between rainfall. So you are, you want to test if there is actually meaningful change in slope and latitude with different levels of rainfall, or the other way around. And here you could look at the probability distribution of the parameter for the interaction. Alternatively, you can also do a model comparison. And this is what the output of this model comparison is. So if you just say LOO for one model, then you get some output. But just as the AIC, the pure value of the for one model doesn't give you any information. Only by comparing it to another model, you get to know if this the model is better or not. Right, so AIC, and just this one as well, doesn't describe how well one model fits the data. You only can compare it to how well another model fits the data. So it's a relative measure. You can only use it as a relative measure. So here, if you just if you just look at the LOO for the one model, you get all the information, you get the ELPD, or you also get the LU-IC value, and for the LU-IC value here, the lower values are the better. And it also comes with a standard error. The standard error here, now that's a very technical detail. The standard error does not come from the uncertainty in the parameters. Here it actually comes from the standard error of having this evaluated in many data points. However, that's a minor technical detail. However, it comes with some measure of uncertainty, and that's the important thing. Because if you compare two models, you want to choose the model with a lower LU-IC, and the model comparison also already gives you the difference here. So the model 3 has the better value, right? So there's a difference of 3.5 to the more simple model. However, this comes associated with some uncertainty. So this difference also has some kind of a distribution. And then the rule of thumb is you should only choose the more complex model if the difference is more than 2 standard deviations. The LU-IC value is a bit better. However, there's some uncertainty involved, and I cannot be 100% sure that that this model is actually better. So again, for the principle of parsimony, here I would choose the less complex model, because there's not 100% evidence, or whatever, 99% evidence or something, that the more complex model is to be preferred. So you can use this just as ARC. You can compare models against each other. They do not have to be nested. Additionally, it comes with some measure of uncertainty, which allows you to even make better decisions. Okay, so the next part is categorical predictors. I think it's the first time we have categorical predictors. We had only continuous so far. Yeah, I think so. So we start with a simple example where we have just a predictor with 2 levels. So here the data set is bird species richness in different habitats, and habitats have different landscape types. So the whole data set there is 4 landscape types: agriculture, urban, bauxite, I think that's former mining sites, and forests. But we will start with a subset, just 2 habitat types first: agriculture and urban. So we want to estimate if there's a difference in bird species richness in agricultural sites and urban sites. So in frequentist statistics, this would be a classical t-test, where you have 2 distributions and want to compare their mean, right? So frequentist t-tests, just as a reminder, it doesn't calculate if there's an overlap in distributions. It doesn't care if there's an overlap in distributions of the data. It only tests the difference in their means. And if you remember this nice slide with all the kind of, all the statistical tests are just linear models. So this is the most basic one. The t-test is a linear model. It is a model for a categorical predictor with 2 levels. So you would fit a model here which has 2 parameters, and these are the kind of level-specific means of the response here. So one mean for agricultural sites, one mean for urban sites. And the stochastic part is that all the data points are normally distributed around their respective level means. So altogether we have 3 parameters, because we also have a standard deviation here. And you want to estimate and also, most importantly, compare the group level means. Classically, LM and GLM and also BRMS uses one specific way of coding this. So the parameters you fit or the parameters you will be see as an output are not both group level means, but you will have something like an intercept and something like an effect. And you can achieve this by rewriting the deterministic part of the model by saying or by defining one of the levels as the reference level. Usually it's the one that comes first in the alphabet. Here it is agriculture. So this is the reference level. And for this reference level here, we have an intercept, which is B0. And then the prediction for the other group is intercept plus the difference. And you can achieve this by dummy coding this. So you have a variable which is either 0 or 1, and it depends on if the landscape is agriculture or urban. And then this can be kind of seen as a classical linear model. And then here the predictor is treated as if it was a continuous predictor. But the model structurally, I mean, is identical. The predictions are the same. So which also means that the likelihood is the same for both models. It's just the reparametrization. Instead of having two intercepts, we have now one intercept and the difference to this intercept. And this is the default in BRMS as in other environments. So if we just model S independence, so the species richness independence of landscape, then the output will be an intercept and the difference. Here, this has the advantage that at least in this simple model with two levels, that the difference, we don't have to calculate it. It is already a parameter. So we see, okay, the mean difference in species richness is 8.77, and we already get credible intervals for this intercept. Sorry, for this difference. And we can directly, for instance, with a hypothesis function, test if this difference is different from 0, which in this case would be the same as testing the mean of urban habitats versus the mean of agricultural habitats. However, if you don't want to have this dummy coded, but you actually want to have the predictions or the intercepts as parameters in the model, then you can do that by specifying -1. Alternatively, I think you can also specify it by writing 0 plus landscape. This means no kind of intercept and then fitting landscape level variables only. And then you directly get all the estimated means as parameters. However, if you then want to compare them or look at the difference, you have to calculate it. Again, it's the same. For the models or for the parameters, or for the outcome, it doesn't make a difference. So here, if you want to compare the mean, you have to explicitly write this in the hypothesis function to look at the differences. And remember, what we are not doing is looking at the mean estimate of the first and the mean estimate of the second and calculating the difference. Here, this is kind of, it's working out because it's all linear, but in general, it is not. So what we are doing is we are computing, or we are looking at all the posterior samples of landscape agriculture and all the posterior samples of landscape urban, which means for each of the samples, we are calculating the difference. So we get here 4,000 difference values, and then I can compute the mean from that for the mean difference and also its distribution. So this was the kind of classical t-test in frequentist statistics. You have just two levels in your predictor, and you want to compare if there's a difference in means. If you have more than one level, so different groups, you have one predictor with k levels, then in classical frequentist statistics, you would fit an ANOVA. It's called analysis of variation. The model, stochastic and deterministic part look the same. However, mu of landscape, so mean for each landscape level, now has 4 parameters because there are 4 different group means, and additionally 1 parameter for the standard deviation. So the goal here is to estimate and also to compare the group level means. In frequentist statistics, you would make an F-test, and the null model is that you just have one intercept, or they are all the same. So that's the null model, and you test this against the model you are fitting, that they all have their individual mean. Yeah, so you're basically testing against the null model where all are the same. How does this model look in detail? Again, here the default is dummy coding. Here for each level of the predictor, or for each additional level, apart from the reference level, another variable is introduced. So this is kind of weird and also, I would say, not so easy to understand. So I just wanted to, for the sake of completeness, just show you how it is done. But basically, I think it's sufficient to look at the figure at the right-hand side. You're fitting an intercept, which is the reference level's mean, and then you're fitting you're estimating the differences to this reference level for all the other levels. Okay, so 5 parameters. I mean, minus the standard deviation is 4 parameters. It's the same number of parameters as if I would fit all the means themselves. And if you use this in LM or in BRM, you get estimates exactly for this intercept and for all these differences. So just looking at the parameters here, this doesn't give you any information about this kind of F-test. It just gives you the specific differences to the reference level. So just fitting the model will not give you an answer in the sense of an ANOVA, right? So it doesn't give you automatically, oh yeah, they are different, or there are differences such that this model is better than fitting just the intercept model. So just fitting a model does not give you an overall effect like a classical ANOVA table would do. However, you can just construct it yourself if you're interested in the classical ANOVA type analysis, which means you fit the model where landscape is a predictor. You fit a second model where you just fit an intercept for all of them. So the model is just S tilde 1. So you're just fitting the intercept. And then you perform model comparison. So this would be the analysis in BRMS on the Bayesian framework if you're interested in this, or if you want to have this one test for all the differences at once. Okay, so here the answer would be okay. The fit with different landscape levels is the better model. There's a difference of 27 in this leave one out model comparison. and associated with the standard error of this measure, I'm still pretty confident because it is the difference is larger than 2 standard deviations. So sometimes here you, instead of having like this classical test for some specific question, you start with your question and then you propose 2 different models that relate to your question. The one is the model with the landscape predictors, and the other would be the other model where they are all the same, and then you can compare them against each other. So we can always kind of fall back to comparing models that relate to your questions. We have different choices of modeling if we have 2 predictors. So if you have just one predictor, we can just include the predictor or leave it out, right? So there's not much of a choice there. But if we have 2 predictors, there's different model choices. So think of, okay, we have again the same data set, but now we also want to correct for area size. So the data we observed in each habitat is categorized in two size classes. I think the original data set has the actual size, but if in your data observation process you just note down, okay, is it large or small? You do not have access to the actual size anymore. Then we have the situation where here we have 2 factorial predictors. And sure, area influences species richness, so we would want to include this in a model. And the first model would be to just add this as an additional effect. So we have landscape plus area. So it accounts for the differences in area size, but this area effect is the same for all landscape levels. And here, this is now specific for this model. This model has to be dummy coded. We cannot write this model by fitting all of the different kind of intercepts for all the level combinations, because this model has less parameters than their level combinations, right? So here are 8 different level combinations, but we only have like 4 landscape levels and 2 area levels. So we don't have enough degrees of freedom to kind of fit all the means independently. That's just not possible. So here internally, or for the model itself, we cannot use this mean coding. We actually have to use dummy coding. The second one, this interaction model. And I always think of the interaction model in terms of not dummy coding it, because then for me, it's very simple to understand what it's doing. If I fit the interaction of all the predictors involved, this just means I'm fitting an independent mean to all the different level combinations. Yeah, BRMS will per default dummy code it, but conceptually you can reparameterize that all of the different combinations, here's all the different 8 combinations, will get their independent mean. So let's start with the first one. So this is now the dummy coding notation. And it will not fit independent group means because the model itself does not have enough degrees of freedom. Yeah, so if you fit the model, you again will have an intercept. Now this intercept is the estimate of the reference levels for both predictors. So here this would be the mean for landscape agriculture in a small area. So there's 26, which you can see on the right side, which is the red points to the left. So this is the reference level. and now you get either for differences in landscape or for the difference in area, you get different effects. However, there is no interaction. And therefore here all the lines, so all the area effects are parallel. So here you would fit this model if you would have the question, is there an additional effect of patch size? So patch size here only has one parameter, so you can directly look up the effect, right? So the average effect of being in a large habitat is plus 7.2 species with some uncertainty involved. So here you wouldn't even need to do a model comparison, but you could if you want to. So fit the model versus the compare the model to the reduced model where area is not involved. Right. So here we could just look at the area effect because area just has two levels, then it's fine. Or we can do the model comparison. Another question would be when I'm correcting for area size, are there still differences in landscape types? And here the summary table again is not helpful. Here we would have to do a model comparison of the two models that relate to the question here. Then finally, we look at the full factorial model. So if we are interested in, or if we assume that the area effect is different in different landscape types, we wouldn't be able to answer this with the additive model from before, because here per default, the area effect is the same. But if we want to test if the area effect is different in each landscape type, we can fit the full factorial model. Again, the dummy coded model looks kind of nasty. We also get dummy coded new variables for all the combinations of predictor levels. However, conceptually, if you look at the last line here, I always think of this full interaction model as having an intercept, which is depending on landscape and area. And since we have since we have 4 and 2 levels for both of the predictors, we have in total 4 times 8 means which are fitted. However, again, if you just fit this model with this interaction term, the output is this dummy coded, which now really is quite difficult to read. I usually just look at this table to see, okay, if the model is converged. I do not even look at this collection of, for me, meaningless values. So here you definitely should translate your research question into something you can get from model predictions or from model comparison. So here, if the question is, does the area effect change between landscape levels? Then I compare this full factorial model to an additive model where the area effect does not change between landscape levels. So you see here the lines are not parallel, so the fitted model suggests that there is some difference in the area effect. However, if you do a formal model comparison, you see, okay, maybe the effect is not strong enough to actually support this more complex model. So here this fit factorial is slightly better than the additive model. However, this 0.7 difference compared to the uncertainty of this difference means that we we can't say for sure that the more complex model is to be preferred, so we leave it as the a bit less complex model, so the additive model here. So here the additive model and the factorial model in comparison. Sure, the factorial model allows some differences in these effects per landscape level. However, these differences are assumed to be so small if you look at the model comparison that we actually prefer to use the less complex model. So there's no strong support for the area effect being different in the landscape levels. Okay, I think this is a good time to introduce what sometimes is referred to as post-hoc analysis, because often you want to either summarize or compare different levels here if you have kind of research questions that have a bit more kind of a specific nature. So you want to specifically look at where are the differences and have something you want to test there. You can always do predictions in BRMS and just manually sort out which predictions you want to compute, or you can use tools that facilitate this for you. So we have seen with, for instance, the model comparison, we can see if there is a difference between some group levels, but it doesn't tell me, so the model comparison itself does not tell me where the differences are or which differences are there. It's the same in ANOVA in LM, right? So if you just run the ANOVA, the result is, yes, there are some differences between levels, but you do not know which are different. Sometimes some of these, if you have like 10 levels, sure, some of them are very similar, some of them might be different. By just fitting an ANOVA, you will not be able to answer this question, which ones are different. Therefore, after model fitting, you have to like compare some predictions. And this is usually done model-based, right? So you're not just fitting subsets or empirical group means and comparing them. No, this is model-based. So with the model you selected as the best fitting model, you compare model predictions and associate this with quantitative measures like probabilities. So these questions, here are some examples. For instance, what is the mean species richness in small areas? Yeah, you would have to average over landscape levels, right? So some measure of average here of all the points here and the uncertainty here on the left in the small areas. So you're not only interested in this average, you're also interested in this uncertainty. So you always should have a measure of uncertainty or some spread or some credible intervals of all these quantities. Okay, let me see if I can answer this. Why does the model in the interaction have larger sites have a larger error than the additive model? Okay, yeah. Okay, yeah. So here some of them have a higher uncertainty than the other one. On the right-hand side, you see some high uncertainty, for instance, the urban and the large sites. However, it has less uncertainty in the additive model. The answer here is that the full factorial model basically fits all the level combinations with the independent mean, right? So here you have eight means which are basically fitted independently. The only thing that connects them is their joint residual error. However, in the additive model, they are all connected. So here the area large urban is also informed by the area large, so by the area small urban, because we know we have like a difference there, and the difference is also the same across all kind of landscape levels. So this mean here of landscape urban area large is also informed by all the other ones. It is not independent from the other ones just because of how the model is constructed. Okay, yeah, again, some other questions regarding averaging. For instance, what is the mean species richness in urban landscapes? You would have to average over area size, or you would be interested in the difference between urban and agricultural landscapes. Again, you would have to make some averaging over area and then differences over landscapes. And all of these questions can be answered either by doing the predictions yourself, averaging, or subtracting. But we can use some package for this that makes it much easier. So in theory, you can make all these predictions yourself. You have the parameters to make the predictions, or you can use the predict functions and go from there. And everything kind of downstream from there will have a distribution. So for all the quantities, for instance, averages or differences, you can always extract the distribution and also, yeah, have a probability distribution there for this. But this can be very, very tedious if you want to compute all of this yourself. But we are happy that we have some packages that automate this for us. That's, for instance, the EM means package, which works not only with LM and GLM, but also with BRMS, which is pretty cool. Alternatively, there's the marginal effects package. I must admit, I never have gotten into the usage of marginal effects package. I think what I see from people using it is very powerful. But for me, the EM means package is just a bit easier to handle. So I've been just sticking to the EM means package so far. Okay, we are going back to the more simple model with just one predictor. So species richness depending on landscape. Yeah, if I just fit the model, I just have this dummy coded output. And the first question would be, okay, what are the actual group level means? And you can do these predictions yourself, or you can just say, okay, use the EM means package. And so the first EM means package fit landscape means first you put in the fit object. And second, landscape, this means that for all the levels of landscape, I want to extract the mean. So here it automatically computes the group level predictions. So this corresponds to the black dots you see in the figure here. And again, everything comes with a associated uncertainty. So here the lower and the upper are the 95% credible intervals here. Okay, so this just extracts or computes some predictions. We can have different questions or more detailed questions for the model. For instance, what is the difference between species richness in forest and urban landscapes? And you can apply the pairs function to the EM means package. So here I use this pipe notation where the pairs function is evaluated after the EM means function, but you can also just say pairs of EM means of, and that's the classical R notation. So the pairs command from the EM means will compute all the pairwise comparisons and also their uncertainties. And again, this is done with computing for all the samples from the posterior, computing the differences and only then extracting the means. So here we get a mean difference of 5 dot something and its associated uncertainty. So if you have multiple predictors, again, sorry, there's a typo. So this is yeah, this is the additive model. So landscape plus area, but in the means oh no, sorry, all good, all good. It's all fine. I was confused. So we have the model which is landscape plus area. So if I correct for the area effect, is there a difference still in landscape or the other way around? So again, the summary table wouldn't give you meaningful output. But if you just want to extract the predicted means, you can use means. And even if the model says landscape plus area, if you specify you want to extract the means for area times landscape, this just means I want to extract all the predictions for the combinations of area and landscape. This was why I was confused, because there was a plus in the top line and the multiplication sign here in the means. No, but this is the landscape plus area model, and I want to extract the means for all level combinations. If you just want the means for area, so here is area and landscape combinations, but here just for area, then the model will average over the other predictor. So it will average over landscape, and here you will get the average prediction for small landscapes independent of averaged over all types of landscape. And you can also use this, for instance, to calculate the difference. The same as if you want to average over area, you can just display the means of landscape levels. It's the same, but the other way around. And again, the pairs would give you all the pairwise comparisons there. If you want to compare the mean between forest, or the difference between forest and urban, averaging over landscape. Averaging over area. All right. Okay, now comes the last part. And this is categorical and continuous predictors. Your analysis often will contain both categorical and continuous predictors, and there's different ways of combining them. And often this is called ANCOVA, analysis of covariation or covariance. So we have the same data set again. In the previous example, we just had a categorical predictor area, large or small. But if you have better resolved data, you can use this as a continuous predictor. So the questions could be the same as before, but now you want to account for that you actually have the continuous predictor area, and here you would potentially use log area as a predictor. So here's just a plot of the data. So here on the x-axis is log area, and you see for each of these different levels, there seems to be a positive relationship, and we can fit a model that will generate 4 different regression lines. But depending on using the additive model or using the factorial model, these regression lines will be a bit different. So for the additive model, this will just fit one slope for area. So the slope will be the same for all of these 4 panels, but the intercept is allowed to be different. Whereas in the factorial model, basically fits an individual regression line with an individual intercept and also an individual slope for each of these panels. So in this additive model, now only the intercept is changing and the slope is identical. Again, this is dummy coded for the intercepts here, and the output of your model will be dummy coded. So yeah, the slope, that's actually the meaningful parameter output. So the last line here, log area, this is the slope, which is the same for all of these panels. However, for the intercept, we get this dummy coded, where intercept is just the intercept for the reference level agriculture, and the other ones are the differences in the intercept. Yeah, and you can test for, is there an actual difference in landscape types while accounting for area size? Accounting for area size means I have to include area as a predictor, and then the difference in landscape type would just be a difference in the intercepts here. And this would mean I fit this additive model, which allows different intercepts, versus a reduced model, which just fits one regression line for all of them. So this is the, if you look at the, what I noted down there in red, the last line, this would be the reduced model, where S is just depending on area. And here the answer is clear, yes. Also, when accounting for log area, there's a difference in species richness in landscape types. Yeah, plotting them all in one, you can nicely see how the slopes match, but the intercepts are different. Again, this model comparison only tells you if there is a difference between kind of mean levels of in habitat or in landscape type. However, if you are actually interested in specific differences here, you can use the EM means package again. So here, EM means of this for the landscape variable gives you the actual intercepts here. And you can extract their pairwise differences. For instance, if you're interested in a specific pairwise comparison, also with the EM means package. And the last model we are using here is the interaction model. So why would you use this model? For instance, to answer a question like, is the area effect different in different, is the area effect on species richness different between landscape types? So we would be interested if there are actually different slopes here involved. Again, the summary table here alone will not give you a satisfying answer, but you can use model comparison. And here in this case, even if you see some differences here in the intercepts, the model comparison will reveal that yeah, the data actually doesn't support such a model where all the slopes are different. So I wouldn't use the more complex model and would go back to the additive model. And the answer would be no, the data does not support the hypothesis that the species area relationship is different between landscape types. Here the lines, they are not parallel, or there's a kind of, you see a slight effect, but this effect is so small that we don't think that it is meaningful. However, if you were interested in differences in slope, the EM means package also has a function for comparing slopes, and this is EM trends. You can use it exactly as the EM means function. However, I think you have to specify the variable for which the slope is to be extracted. Here, this variable is log area. And then you can extract, for instance, all the different slopes and also their pairwise comparison, meaning their difference. Okay, so this was a very long introduction to linear modeling in general. All these terms you usually hear, regression, ANOVA, ANCOVA, and so on, these are just linear models. Exactly that all these kind of F-tests and so on, they are basically all just linear models. So you can use them in Bayesian statistics as well. Here, linearity is not that important. However, you only should kind of use a more complex model if you have a good reason to do so. In Bayesian statistics, you should check your model assumptions. And the model assumptions for linear model, we covered them already. Are these kind of 4 steps: independent observations. The model should follow this linear trend. The standard deviation is normally distributed. The residuals are normally distributed, and also the standard deviation doesn't change. However, in Bayesian statistics, we can easily relax these with some remedies and some tricks to account for that. Yeah, so basically, I mean, as a general recommendation, often people are so trained to working with these kind of F-tests, ANOVA, and so on, that you kind of think of, okay, I can do an ANOVA or whatsoever. But actually, you think in terms of the question you actually have for the data. What is the research question you have? And then you can usually translate this research question to some kind of test. And tests now, I mean, very general. Right? I don't mean like a specific test statistic, but in something you can quantify, for instance, a comparison in predictions or a comparison in models, and so on. And even if the linear modeling framework is kind of well recognized and you can do all of this in LLM, I think BRMS offers a very flexible framework here to do all kinds of analysis with a linear model, and it connects nicely with other packages like the EM-means. Okay, I think I'd like to continue. Yeah, so we are coding some classical linear models. I think the same data sets or the same analysis we also have seen in the lecture, but I just wanted to show you then how to yeah, make all these analysis and work with the EM-means package and so on. So we start with the global plants data set again. Here I use the scale command to scale my predictors, so latitude and rainfall. So that the mean of both of the predictors is 0 and the standard deviation is 1. Okay, so here the model would be, again, I want to look at the latitudinal gradient of plant height, of log plant height, but I'm correcting for rainfall. So I'm not going that much into prior choices here. Again, you can always do prior predictive checks. We have seen how this works. Here, I'm using some very general and yeah, weakly informative expectations. So since the predictor value here are scaled, and also the response value here, the The values here are in a reasonable range, here between -2 and 4. I code my expectations here in, I would say, weakly informative priors. So I expect maybe there is a negative relationship of plant height with latitude, and there is some weak information from my expectation that there's a positive effect on rainfall. So this is an additive model, so I'm just correcting for the effect of rainfall, and I do not expect that the effect of latitude changes with different levels of rainfall. So the slope will be identical here across different levels of rainfall. Yeah, first of all, I just look at the model plot. I check the values here, but usually, yeah, with this kind of data and just very simple linear regressions, I don't expect that I'm encountering any serious problems here. Also here, all good. Now you can use the conditional effects plot. Again, I say points equal true, and I specify point arguments to, for instance, plot them in a transparent way. And this will give you an output for both of the predictors. So it produces two figures here. The first one is the effect of latitude, and the second one also here's the effect of rainfall. And since there's two predictors involved here, the value of the second predictor, or the predictor which is not shown, is automatically chosen at its mean value. And here the mean value of the second predictor was 0 because we scaled it. And also here, remember, there's always the second predictor involved. We always have to choose a value for the second predictor if you want to make predictions. And here it is just chosen to be at its mean level. Yeah, if you don't specify anything here in the conditional effects about the variables, about the effects, then both of them are plotted, right? But if you also specify the effect, then you get the individual plots here. You can choose to plot this for different levels of the second predictor by specifying here predictor 1 and the interaction with predictor 2. We know there's no interaction effect in the model. This is just a notation for saying, okay, I want to plot also the effect of the second one. And then by default, BRMS chooses to use the second predictor at its mean. Here this is 0 and plus and minus 1 standard deviation. And since this is an additive model, the slope doesn't change, but the intercept here changes. Note that in the previous figure, we also had some confidence intervals here. So this is the uncertainty of the of this regression line. Here I switched that off just for to make it for visibility by specifying probability equals 0 here. So this is the confidence level for which this is plotted. If I remove this, the uncertainties is plotted, but then the figure at some point becomes quite unreadable. So if there's many lines involved, I switch that off to have a figure which I can read much better. Yeah, so here I'm plotting the effect, or I'm plotting latitude on the x-axis by specifying this first. If I switch that around, so I specify rainfall as the first one, and in interaction with latitude, then I get the other picture. where I have the effect of rainfall for different levels of latitude. So additionally, to check if the model represents the data well, there's these classical figures I would check. So there's the posterior predictive check, where I compare the histogram of the data versus histograms from predicted data. There's some kind of structural difference here. And again, you could try to find other predictors that maybe model this a bit better to get a better correspondence here. But otherwise, there's, I mean, the range is the same and so on. Just here in the middle, there's some minor discrepancy. Yeah, now the observed versus predicted plot. So we have two predictors here. But is observed versus predicted, you can always draw in one plot, no matter how many predictors you have, because both of on the y and on the x-axis here, these are both the response values, here for the observed response and here for the predicted response. And then you have this this check model function from the performance package, and again some classical analysis here. So this is the residuals, which should be kind of, which should not show any kind of trends against the fitted values. And here also the same, or this, yeah, the residuals, but all made positive. And yeah, if you see a clear trend here, an increase or decrease, this would be hinting at some non-constant variance, but I don't see any reason to be concerned here. I mean, the line here is a bit wiggly, but I don't see a clear trend here in that the residuals increase or decrease. Okay, coming back to our research question. So maybe you want to compare different scenarios here. Because note that there's some correlation. And so this is both predictors plotted against each other. Right? So you see there's a negative correlation. There's less rainfall at higher latitudes. So yeah, just the pure effect of latitude or the slope of latitude can be misleading, because it would mean, okay, I increase latitude, but I keep rainfall constant. And if your predictors are correlated, you could, for instance, compare different typical locations here. For instance, here, this is the mean. So the mean latitude and the mean rainfall. And the other would be maybe a tropical scenario where you're close to the equator, right? So here, I think at -2 around, this is the equator with a high rainfall. And both of these points are different in their latitude and also in their rainfall. And you would be interested in comparing the mean plant height between both of these location or combination of the predictors. Right, so you want to compare predictions between these 2 points. We can easily do that by using the fitted command, or by the this other command, which is called posterior epred. In both cases, we have to say, okay, new data is a data frame where I specify both of the predictor values. So here, the first one, this is a tropical scenario where latitude is at -1.5. So this is close to the equator with a typically high rainfall. And the other one, this is just the mean. In this case, this would be 0 for both of them. So if I just plot the fitted values, I just get their mean predictions, but I actually want to extract the full posterior distribution for them to compute their difference. And I can do that, for instance, with a posterior EPRIT function. It has the same arguments, and I will get a long vector here for all of the samples of the posterior, 4,000 predictions, which I then can pairwise compare against the predictions in a tropical scenario. So here, this vector would make these pairwise differences for each sample of the posterior distribution, and then I can look at the histogram. And I can extract the mean, or I can extract quantiles. So here I'm very certain that there is that the difference is larger than 0, and the mean expected difference is 1.6. If you're not so certain about that the difference is actually positive, you can, for instance, just count how many of these predictions or of how many of these differences here are positive, or you can use the hypothesis function. Again, you have to make predictions and then put the predictions in some data frame. So both of the mu's here are in one data frame. Yeah, I have to assign some names. That's what I forgot. Yeah, so you have a matrix or data frame where here you have the predictions for tropical, here you have the predictions for the mean, and here are all the predictions for all of the different samples. And then you can put this in the hypothesis function to calculate the probability and quantiles and so on for this. Yeah, and the plot again gives the same output here. Okay, very briefly, I just want to show you how I did it with the interaction model. Oh yeah, that's a good point. So if you scale your predictors, you can only make predictions with the predictors on that scale. This is true. So you want to make a prediction for some specific degree of latitude, then you would have to convert this specific degree of latitude again you have to subtract the mean of the data and divide by the standard deviation of the data to make this prediction. However, there's an easier solution for that. Because let me check that. So here I scaled the predictors first and then used them as new predictors here in the model. And then the predictions have to be done with the scaled predictors as well. However, I can also directly write this like this: scale latitude plus scale rain. I quickly fit the model. It should be, oh no. So what is going on here? The predictors are now on original scale, latitude and rain. Internally, brms scales them. And also the parameters are, the output then is for the scaled variables. But if you want to make predictions, you can then use your original predictor values. Also here, for the output, the plot is done on the original scale here. So even if the model kind of works on the scaled version of the predictor values, the output here is generated for this. Yeah. I always would work like this, not with the other one, because it's just much more convenient. Yeah, just wanted to use the other one because then you see in the plot, okay, the mean is the 0 and so on. You can see that it's actually on the scaled level and so on. But for practical reasons, I would always use this version here. Yeah, the same here as the interaction model. I could just use scale of let and so on. Just be aware that here then the coefficients have a different name. I think it's called scale lat. Yeah, but especially here with this interaction, either by using scale predictor values or by using the scale function in the model formulation, this is quite, I would say, convenient, because then I have good ideas how to specify priors also for the main effects now. Because I mean, if the predictors aren't scaled and you have an interaction, I have no idea how to choose good priors for the main effects. So the main effect of one predictor is the slope when the other predictor is 0, right? And this could be far out of your actual data. So I wouldn't know often how to specify a good prior there, but by scaling a variable, so either way, you know that the main effect is the slope of this variable when the other predictor is at its mean. And here, so this for this model here, this means I can use the same priors as before, and I have a weakly informative prior, or yeah, very weakly informative prior on the interaction, because I have no idea if the interaction is positive or negative. So I center it, the prior around 0. And again, here checking the model convergence, this looks fine to me. And if you want to plot the model predictions against the data, for instance, with the conditional effects plot, here it's now useful to actually plot this interaction here. So either with z lat as on the x-axis, and for different levels of the second predictor, you see the slope, or the other way around. Yeah, so if you have this interaction model and you are fitting the model because you are interested in the interaction, right? So you that's the thing you are actually interested in, is the effect of rainfall. Does it change with latitude? And here in this kind of special case, this can be answered from the model here alone, right? So this is if this is different from 0, this interaction is different from 0, then I can argue that the effect changes with the second predictor. So you can just check with the hypothesis function. I plot this as well to show you that we are not so super certain here. Right, so is there a positive interaction? Well, the mean effect is 0.2, around 0.2. However, the probability that it is larger than 0 is just around 90%. Right, so here this distribution overlaps with 0, and we are only 90% sure that it is positive. Yeah, so I wouldn't be too sure about that. If it would be like 98%, yeah, I would be sure, but this is an evidence ratio of 10 to 1, so we are not all too certain that this interaction is actually meaningful. Additionally, you can also do model comparison. And here the model comparison against a model without interaction tells you, okay, the difference is very small, but it's very small compared to the uncertainty. So I wouldn't go for the interaction model. There's not enough support for the interaction model in the data. Yeah, so the next thing I want to talk about a categorical predictor, and specifically to check what the prior means in this case. So we have another data set now, that's the bird data set, and here we have the 4 landscapes and the species richness. So you can fit the model just classically, like species richness versus landscape, or you can, so this will be dummy coded, right? So where you have the intercept for the reference level and then all the differences to the reference level. Or here for this model, you can enforce to not dummy code it by putting a 0+ landscape here. And for both of them, the prior specification means something different. We can check this without fitting the model by just using default prior. Okay, so there is some prior for the sigma, that's fine. And then there's some prior for the intercept. Okay, what's the intercept here? Well, the intercept is the mean of the reference level, right? So for the agricultural level, we get an prior for this mean here in the reference level. And then the other ones where we don't have any priors, these are the differences to the landscape level. And they do not come with any priors per default. So you could fit this model with some prior for the differences. So how much do you expect that that something deviates from the reference level? The other model, on the other hand, if you do not have an intercept and you fit all the group level means directly, here the prior are a bit different. Again, you have prior for the sigma, but now all the effects are the actual means in the in the group levels, and they don't have any priors. So if you specify a prior for this one, this should be reflected that you actually specify a prior for the means, so for the species richness, and not for some deviance or some difference from the reference level. So keep in mind that if you, I mean, and usually you will fit it with a dummy coded because then you have a bit more flexibility. And note that the priors for the effects mean that the effects are the differences to the reference level. Right, so yeah, centering them around 0 is a good idea because like the differences can be positive or negative. Yeah, and this is the standard deviation here is a measure of how much they are allowed, or how you think they are deviating from the reference level. If you specify, or through the priors, both of these models are not exactly the same, because they have even if you don't specify priors, through the default priors, there's a tiny bit of a difference between both of these levels, but just through the prior information. However, I think this difference here is very, very marginal. So technically, both of these models should give you almost the same results. Okay, I'm skipping the looking at the model output. I'm just seeing, okay, the R hat values are all good. If you plot the effects, then you, even in the dummy coded model, you will see the group level means. So, okay, so this is an ANOVA type of analysis. You could compare this to a model where you just fit the intercept to see, okay, if there's actually support for that there's a difference in all these levels. We're skipping this now. Here it looks like I'm pretty sure that there's a difference, right? So they're clearly different. And you could you could use the EM_means package to extract these differences. So here we are in the postdoc analysis after fitting the model. So usually the ANOVA tells you if there is a difference, and you have to actually use EM_means or some other methods to tell you where the differences are and how strong they are. So the EM_means just extract all the mean values. So these are the mean predictions. These are the same. So these correspond to the dots here in the figure. And by using the pairs command, you will get all the pairwise comparisons and their associated uncertainty. So if you're interested in specific differences, you can extract them here with the EM_means package. And here I just showed you that if you want to make a fancy picture with it, you can use all your ggplot knowledge. So this conditional effects can be extracted, and then you can, for instance, here put in the differences in how much the differences are connected to these lines, and I mean whatever you want to do in ggplot. So let's see. I will briefly talk about the two-categorical predictor model, and the rest of the analysis I would propose you can have a look at yourself. So again, this is the same example as in the lecture. Again, species richness, different landscape types, but now you have small and large areas. And yeah, if you are interested, again, are there differences in landscape type while correcting for area size? You can fit this as an additive model. So here, actually, this additive model has to be dummy coded. You cannot kind of enforce effect coding here. If I use this, I think you should get an error. Oh no, it does something, but I think the output will be completely nonsense. I haven't checked it. I'm curious what the output will be. Okay, yeah. So it used effect coding for the first one, so you get the actual kind of levels or intercepts for all the different landscape levels, but at area equals small, and then there's this dummy coding for the other one for the area. Okay. Yeah, but still, there's some dummy coding for area involved. You cannot get rid of this by in this additive model. So let's refit this in this classical dummy coded way. Then both of these predictors are dummy coded, which means you have some overall intercept, which is the intercept for agriculture in small patches. And all the other ones, all the other parameters describe differences. And for them, I specified a prior here. So I said class equal B without specifying a coefficient. This means for all the differences, for all the all of these parameters, I chose some prior here for all the kind of effect sizes. Yeah, and here I could answer this question if there's a difference in landscape levels, or if the area effect is difference between landscape levels, I can also fit an interaction model. And that's basically it. I mean, we covered all of this in the lecture already, but here's just some ways to nicely plot these things. yeah, and also work with the EM means package for all the questions we also covered already in the lecture part. I think there's nothing else new involved here. No, that's all. It's all been covered. So we covered that. Yeah, there's an ANCOVA type of analysis. You can try to model a full data set where you have the log area instead of just a large or small. The priors are or can be a bit tricky, especially maybe in the interaction. So first try coding these models, maybe without the priors, and then maybe have some suggestions. Otherwise, you can always look it up here. Additionally, I mean, we already have all the tools you need for linear models. So if you have a data set at home, which would fit a linear model analysis, you can already check and try to work with this. Additionally, there's this nice data set, the Palmer penguins package, which has this nice data set of a couple of penguin populations with all kinds of covariates involved. So you can choose some relationships you model there, and usually I think they should all be fine to model with in a linear modeling framework.